Hello, I'm Chavis von Bradford. Today, I'll be talking about how chemistry and to some degree electrical engineering are used to detect the cosmic microwave background, which is the remnant radiation from around 308,000 years after the Big Bang. And the Big Bang has inferred to have occurred around 13.78 billion Earth years ago. And this is critical for our understanding of the early universe as well as any pre-Big Bang phenomenon. Many other apparatuses, such as the Large Hadron Collider, COBE, and WMAP, have contributed to our understanding of the early universe, and there will be future apparatuses from the European Space Agency, such as LISA, or the Laser Interferometer Space Antenna, and the 双星政府电子对讲机, which is the Circular Electron Positron Collider from Zhengguo. However, today I will be focusing on the European Space Agency's Planck Space Observatory. Now, I will be focusing on the Planck Space Observatory's materials and components and their roles in detecting the cosmic microwave background based on a specific paper named Planck Pre-Launch Status, Design and Description of the Low-Frequency Instrument by M. Bersanelli et al. Before I focus mainly on gallium arsenide and indium phosphate, I will list some other chemicals as well and how they contribute to detecting the cosmic microwave background. But this will be in a lesser degree for time constraints. But focusing back on gallium arsenide, it is a dark gray crystalline compound containing gallium and arsenic. And it is used to manufacture microelectronic components such as solar cells and semiconductors. Gallium arsenide is used in the high electron mobility transistor amplifiers, which increases the strength of the weak and distant cosmic microwave background signals. Gallium arsenide allows electrons to move quickly, allowing these amplifiers to have highly efficient and highly capable handling of high-frequency signals. The electron configuration of gallium is AR 3D10, 4s2, 4p1, and that of arsenic is AR 3D10, 4s2, 4p3. The electron shells and atomic orbitals of these elements contribute to their electronic properties through the distribution of electrons in the 4s and 4p orbitals for gallium and the 4s and 4p orbitals for arsenic. Gallium arsenide's ability to detect the cosmic microwave background is influenced by the distribution of electrons in its atomic orbitals, specifically in the 4s and 4p orbitals, which affects its conductivity and band structure, including the direct band gap of approximately 1.43 electron volts. Electron spin, typically plus 1/2 or negative 1/2, and atomic bonds, such as the covalent bonds in which electrons are shared, determine the material's crystal lattice, impacting its electrostatic potential and overall stability. The probability density functions, including the radial distribution function and the angular distribution function, describe the likelihood of finding an electron in a particular location, which is crucial for understanding how electrons interact with the material and the external signals from our early universe. This complex interplay of quantum mechanical properties enables gallium arsenide to have high electron mobility and efficient charge transport, making it suitable for detecting the cosmic microwave background. Indium phosphate, on the other hand, is a binary semiconductor composed of indium and phosphorus. Indium phosphate is another material used in the high electron mobility transistor amplifiers. It also amplifies weak cosmic microwave background signals, but its differentiation from gallium arsenide is that it does this with low noise, and it ensures minimal noise for sensitive instruments. The electron configuration of indium is Kr 4d10, 5s2, 5p1, and that of phosphorus is Ne 3s2, 3p3. Similar to gallium arsenide, the electron shells, including the 5s, 5p, and 4d orbitals for indium, and the 3s, 3p orbitals for phosphorus, and atomic orbitals influence its electronic properties. The electron spin, which can also be either plus 1/2 or negative 1/2, and atomic bonds, such as the covalent bonds that shares electrons, contribute to its crystal structure as well, and electrostatic potential, such as the Coulombic potential. The probability density functions, such as the Schrodinger wave function solutions, provide insight into electron distribution, particularly the spatial electron density, which is essential for understanding its conductive property. Indium phosphate, with its high electron mobility and low noise characteristics, also amplifies weak cosmic microwave background signals, ensuring minimal added noise for sensitive measurements. I will now state some other chemicals and materials that contribute to the detection of the cosmic microwave background based on the Planck Space Observatory from the European Space Agency, although in lesser detail for time purposes. Copper, which are in pennies, is utilized for grounding components like the high electron mobility transistor, providing a stable path for electric currents to prevent interference and ensuring stable electrical connections for accurate signal detection. Nickel, which is also in coins, is used in components like the high electron mobility transistor drain, which adds in efficient signal transmission due to its good electrical conductivity. Manganin, which is an alloy typically comprised of 84.2% copper, 12.1% manganese, and 3.7% nickel, are used in high electron mobility transistor gates and temperature sensors. The manganin measures temperature accurately with stable resistance over a wide temperature range, which is crucial for precise cosmic microwave background measurements. Titanium, which is usually in fighter jets and things that are made of very strong materials, are used in phase switch components, helping switch the phase of signals. Its high strength and low thermal conductivity make it reliable for phase switching, ensuring accurate signal processing. Aluminum, combined with kapton, shields the instrument against electromagnetic interference and external noise, maintaining a clean signal environment for detecting faint cosmic microwave background radiation. But let's focus more on gallium arsenide and indium phosphate's role in detecting the cosmic microwave background. You see, the Planck satellite mission employs a low-frequency instrument that is used to detect the cosmic microwave background. The low-frequency instrument is tasked with observing the full sky in intensity and polarization in 3 frequency bands, which are centered at 30, 44, and 70 gigahertz. These observations are crucial for studying the cosmic microwave background. Gallium arsenide is integral to the low-frequency instruments amplifiers, which are devices designed to increase the strength of weak signals. Specifically, the low-frequency instrument utilizes gallium arsenide in the monolithic microwave integrated circuit amplifiers to boost the weak cosmic microwave background signals, allowing for detailed analysis. The monolithic microwave integrated circuit amplifiers in the low-frequency instrument uses gallium arsenide to enhance these weak signals, and it is akin to someone in FL Studio increasing the gain on a waveform that has very low volume. The gain represents a amplification level, while the noise, which can be from many external sources, represents the static or background that is introduced. Detector diodes, particularly gallium arsenide Schottky diodes, play a crucial role in converting microwave signals from the cosmic microwave background into electrical signals for processing by the low-frequency instrument. Schottky diodes are chosen for their fast response and efficiency. Gallium arsenide Schottky diodes also convert the amplified signals into an analyzable form, kind of similar to translating a foreign language. Additionally, indium phosphate technology, a compound of indium and phosphorus, is employed in some of the low-frequency instrument components due to its low noise levels and suitability for cold temperature operation, which is essential for cosmic microwave background detection. Now, I never really explained what high electron mobility transistors are, but they are a type of field effect transistor that is designed for high frequency and high-powered applications. Indium phosphide is utilized in high electron mobility transistor amplifiers, which further amplify the cosmic microwave background signals with minimal added noise, particularly in the 70 gigahertz receivers, ensuring optimal sensitivity and high performance. The low-frequency instrument consists of an array of microwave radiometers utilizing state-of-the-art indium phosphide cryogenic high-electron mobility transistor amplifiers implemented in a differential system using black-body loads as reference signals. The design ensures optimal sensitivity and accuracy in detecting the faint and distant cosmic microwave background signals. The cryogenic operation maintaining the low frequency instrument at around 20 Kelvin, which is around 200 and negative 253 degrees Celsius, is crucial as it enhances the component's performance and minimizes unwanted noise. The advanced use of materials and components allows the Planck Space Observatory's low frequency instrument to detect these faint cosmic microwave background signals. Helium-3 is used in the Planck's dilution refrigerator for the high-frequency instrument, which I haven't really talked about, yet the low-frequency instrument was cooled by helium-4. Now, lower temperatures reduce unwanted noise, allowing for a more accurate detection of these weak and distant cosmic microwave background signals. Various design considerations are placed to minimize errors, addressing potential deviations from ideal performance, such as non-ideal receiver components, thermal fluctuation, pointing errors, and things of this such. And this ensures the accuracy and stability of cosmic microwave background measurements. But it's kind of weird. You see, the Big Bang in and of itself, and I mean this in a non-anthropocentric manner. I don't mean this in the sense of a pre-Big Bang anthropocentric deity or entity, but the process of pre-Big Bang phenomenon and post-Big Bang nucleosynthesis, which refers to the process that occurred about a few minutes after the Big Bang, and a lot of this has been proven with various particle colliders, have led to the formation of the lightest elements in the universe. And during Big Bang nucleosynthesis, hydrogen, helium, and small amounts of lithium and beryllium were created. And as some of you may know, lithium is used as this psychiatric medicine for grunge metal bands. Heavier elements weren't formed until later. So the irony in all this is that the helium that is used in the cryogenic aspects to detect the Big Bang itself were made in the Big Bang nucleosynthesis. However, these heavier elements had not formed yet because conditions didn't last long enough during Big Bang nucleosynthesis for complex nuclear reactions. So at that time, helium-3 and helium-4 are two isotopes of helium that were produced during this time. Helium-4 making up around 25% of the universe's baryonic mass at that time. However, after eons and eons of time of the helium um, contracting in on itself, stars has began to form, and stellar nucleosynthesis, which is the process by which stars produce elements through nuclear fusion, had began to occur. Over their lifetimes, the stars fuse these lighter elements that already occurred during Big Bang nucleosynthesis into heavier ones. And gallium arsenide is a compound where gallium was produced in stars through the S process nucleosynthesis, which is the slow neutron capture in giant stars, and the R process nucleosynthesis, which is the rapid neutron capture in supernova. And this combines with arsenic, which is mainly found during the supernova explosion in and of itself through the R process. Indium phosphate involves indium, which is created by both the S process and R process in supermassive stars. And phosphorus was produced in massive stars and dispersed throughout the universe due to supernova. And copper was also formed in stars through the S process and R process. And nickel was also formed in this manner, and so was manganese and most of our other elements, but titanium is produced in supernova through the alpha process in massive stars, which is commonly formed during the explosive aspects of nucleosynthesis in supernova. And aluminum is formed in stars primarily through fusion reactions involving carbon and oxygen, and is distributed into the interstellar medium by supernova and stellar winds. And the kapton, which is a man-made polymer, consists of elements such as carbon, hydrogen, oxygen, and nitrogen. They were made during the stellar fusion process. For example, carbon is produced in stars via the triple alpha process. So it's kind of odd how Big Bang nucleosynthesis led to us having the elements to find out that the Big Bang occurred in the first place. But lastly, I'm going to touch on something kind of strange. You see, truck driving plays a peculiar role in all this because you have to transport these materials for scientific research. For instance, gallium is classified as UN 2803 and arsenide as UN 1558. And these are hazardous materials that require special handling during transportation. They require particular placards that have to be put on the four sides of the tanker or trailer. And cryogenic helium, which is UN 1963, which is essential for cooling the instruments like those on the Planck Space Observatory, also need careful transport due to its extremely low temperatures. And these hazardous materials must be transported safely to ensure that they reach the laboratory and research facilities without incident. Now, despite indium phosphate not being classified as hazardous, the safe and efficient transport of all these materials are vital for the success of scientific missions aimed at exploring what happened during and before the Big Bang.